Welcome back, everybody. I think it's time. I'm back in my basement. I'm just going to be writing on my little screen because my arm is still messed up. I hope everybody's doing all right. One little announcement: we have our first test this week on Friday. So for today, we're going to do class as usual, but what we do today will not be on the test. So the test covers everything up through last week on Friday. That is open sets and closed sets. And then, we're going to do new stuff today, but it will not be on the test. And then tomorrow, I thought it would be nice to just sort of do some review stuff during class. So I'm going to make up a bunch of review problems, sort of a little review sheet. And, we can either I'll do them, do some examples for you, or I'll have you guys work on them and see how they go. I have graded all the homeworks so far. I know sometimes I've been a little late doing those, but they are all done now, so you should be able to log into Gradescope and see your results. Please let me know if you ever have any questions about, I said something wasn't right and you're not sure why. I try to write in, comments, but sometimes it's difficult. So let me know and I'd be happy to go over anything. Does anybody have any questions at this point about the test? What's going to be on the test? What's the test going to be? Everything's going to be on the test. Any questions about it? All right, we're going to talk about it tomorrow anyway. So, and for those of you who don't come in person, I will send out whatever review sheet I come up with. I will email it to the whole class too. All right. Any thoughts? Someone give me a thumbs up so I know somebody's listening. Any thumbs? I can't even see the people. I already see a thumb. All right. Thank you for the thumbs. So let's get to it then. We were talking last time about closed sets, and I thought it might be nice as sort of a little exercise or something, example. Let's show that. I'll write this as a theorem, although it's not so difficult to show that any closed interval is a closed set. You believe that, right? Everybody believes that. Any closed interval I'll write it as interval a to b is a closed set. This is just to get us warmed up here. We are going to continue talking about closed sets today, so I just want to make sure everybody remembers what a closed set is. A closed set means it contains all of its limit points, right? So for the proof, we need to show that every limit point of AB, the closed interval AB, is an element of the closed interval AB. So to show any limit point is in there, I'm going to say let X be a limit point of the interval AB. And then we'll show that X is actually in the set AB, right? This is what you have to do to show something is closed. It closed means it includes all of its limit points. So you got to show that if there is any limit point, then it is in the set closed interval A to B. All right. How are we going to do that? We have to remember what it means to be a limit point. The definition was that any neighborhood around X contains some points of the interval AB other than X itself. Or you can say it in terms of sequences, which in my opinion for this example, and maybe for all examples, I usually like to think of it in terms of sequences. So I'm going to say since X is a limit point of interval A to B, this means there is a sequence of points in the interval which converges to X. That's what it means to be a limit point. So since X is a limit point of A to B, there exists a sequence. Let's call it xn in the interval with xn converges to x and xn not equal to x for all n. So this was a theorem that we had last time. It said that a limit point, some point is a limit point if and only if there's a sequence in the original set which converges to that point, and the sequence is never equal. The terms of the sequence never equal that point. That's what it means. Or that was a theorem about limit points. That's why these things are called limit points, because they are the limits of sequences in the set. Okay, so there is a sequence which converges to x. Remember, our job is to show that x is between a and b, or x is in the closed interval a to b. Since xn is in a, b, like this, we get an inequality. I'm going to use the order limits theorem. Remember that? This means a less than or equal to xn less than or equal to b for all n by the order limit theorem. And you remember the order limit theorem? Can someone tell me what does that have to do with anything in this case? That was the one about if A said something like, this is a little sidebar just so you remember, if an less than or equal to c for all n, then a less than or equal to c for, not for all. A is the limit of an. An converges to a. And if all the terms are less than or equal to some number, then the limit is also less than or equal to that number. So what do you say over here? Can anybody see? Somebody shout it out. Unmute yourself and shout it out. I want to hear you shout it out. Oh, say it again. I didn't hear you. Say it again. Sorry.
X is less than equals to b.
X is less than or equal to b. Yeah, that's right. Here we have right here it says xn less than or equal to b for all n, which means x is less than or equal to b. And also the same thing. I didn't write it down over there, but the same thing is true for greater or equals. X greater than or equal to a for all n means that x is greater than or equal to a for the x that it converges to. So by the order limit theorem, we can say this, right? The order limit theorem, it works for less than and also for greater than, so we can do them both at once. X is less than or equal, or a less than or equal to x, less than or equal to b. All right, and what does that mean? That actually is what we wanted to show. We wanted to show x is in the closed interval. So x is in the closed interval a to b, which is what we wanted, right? All of that shows that the closed interval is a closed set. It really is. Anybody got any questions about that? I think one of my problems on the review sheet is going to be show that any open interval is an open set. Totally different proof, but not so difficult. All right. Okay, I hope everybody has their memories refreshed about closed sets. It means that it contains every limit point, and a limit point means it's a point which is a limit of a sequence from that set. You can also say it in terms of neighborhoods. A limit point means that every neighborhood around that point intersects some other points in the set. Okay, let's talk about, this is sort of our big topic for today, is something called the closure of a set. And this is something I mentioned kind of offhand maybe last time. I think it was last time. But I want to talk about it more in more detail here. Remember, a set is closed means it contains all its limit points. A set which is not closed, we can always make it closed by adding in its limit points. So if A is not closed, That means it lacks some of the limit points, right? Because closed means it includes all of its limit points. If some set is not closed, it means it somehow is missing some of its limit points. And if a set is not closed, you can always add in those extra limit points. So we can add in, by which I mean, as far as sets go, we can union in those points. The set doesn't have those points in them, but we start to include those extra points, which, the operation for that in set theory is union. We can add in, by which I mean union, all of the limit points. And we end up with, that says and up with a closed set, because we have included all of the limit points. We end up with a closed set. In specific language here, I'm going to write this as a definition. Anyway, that closed set is called the closure. That's what we're talking about today. So I'm going to say let L be the set of limit points of some set A, and then the closure of A. This is like an operation you can do to a set. You take the closure and you get another set. The closure of A is defined this way. We write it as A bar, and its definition is just A union L. You take all the original points, and then additionally you include all the limit points. That's called the closure of A, and we write it as A bar. Often in set theory, the bar often means complement, but not so in our textbook. The bar means closure. Actually, in topology, the bar basically always means closure. So it's a very standard way of writing the closure. All right. The closure of A. Okay, let's just look at some examples, and then I want to show some fairly simple theorems about the closure. It means you add in all of the limit points. So, for example, here's a simple example. What if I have an open interval and I take the closure? That's the bar means the closure. It means you begin with the open interval. You have all those points, but then you are going to add in the limit points if there are any limit points. What do you think? What are you going to end up with? Waiting again for the people.
Close interval A B.
Yeah, somebody said the close interval from A to B. Yes. That's because the limit points of the interval, the open interval, its limit points are all the points in there plus the A and the B. The 2 points on the ends are limit points. And so when we take the closure, we must include those points also. And what we end up with is the close interval from A to B. Excellent. I have a few more, maybe just because I hear not a lot of people want to talk. Can we do some breakout rooms? Can we do that? Let's try it out. I will actually make some nice little breakout rooms. For these, you may want to look back on your notes from last time. We talked about these sets as examples. Some of them at least. So I have a few examples. Your job in each case is to find the closure. So the first says the closure of Q. The next is the closure of that set, 1 over n. The next is the closure of n. And how about, might as well put a R in there. And then I have a more general question. If F is a closed set, then what can you say about F bar? And then one last thing. What can you say about F bar bar? Those are 2 bars above the F. Okay, in your breakout group, I would like you to discuss each of these things. Let me see if I can do this. I think in Zoom I have to stop my little screen. That's a disaster if that's true. Sorry, can you write these all down? Because once I make the groups, I think I'm going to have to... you're going to lose the picture of my screen there. I'm going to do it anyway. What? Sorry, I'm struggling with the groups here. All right, I'm doing it. You should have all been assigned a room. Once you enter the room, you will lose my screen. So copy those things down before you go in if you need to. Dee, 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 dee.
What do you get?
Would it be all real numbers? That's what I was thinking, but I think only the real numbers that are in Q. Yeah. So then.
Dee, dee, dee.
You're good with this. I tried.
You guys doing all right?
Yeah, we're doing perfect.
Sorry, there's only two of you. I don't know what happened. I think somebody bailed on you. But,
That's okay. Now there's three of us and we're happy.
okay, you're doing great. All right.
I just looked it up. It says that it's already closed, apparently. Maybe that's not right.
You guys doing okay in here?
I think so.
Yeah.
Trying to.
All right.
We're on the natural numbers one.
Okay.
Um,
Any thoughts?
not at the moment.
We didn't actually talk about
No,
that
it's not
example
open.
last time.
Yeah.
But we did talk about this. It's just like the set. I think one example we did last time was the set 1, 2, 3.
Oh, yeah.
That's basically the same
Okay.
in terms of limit points.
So would it just be n? Would it just be the natural numbers?
Yeah, because there are no limit points of that set. Because the points don't actually like accumulate anywhere. They're all just they're all isolated from each other. Okay.
Would that be the same thing for real numbers?
What do you mean the same thing?
Well, for the closure for real numbers, is that like the same thought process as the natural numbers?
Not really. The natural numbers have no limit points. And so when you do the closure, you just get the same stuff again because there's no extra limit points to include. But
R open and closed?
yeah, R is open and closed, and everything is a limit point in R.
Okay.
So would it be R union R?
Yes, it would be R union R, which is
Isn't that just R?
R. Yeah, right.
Yeah.
Yeah. Yeah, another kind of less formal way to think about it is when you take the closure, the set is going to get bigger or maybe stay the same. But R can't get any bigger, right? Because it's already everything. So the closure of R is going to be R again. Yeah. Great. You guys are doing great. Get out those rooms. They're coming back. I'm waiting for everybody to get back. All right, I think everybody's back. Thank you for breaking out. Sounded like people were talking, which is great. What did you think? How about the closure of Q? I listed these in no particular order. Maybe this is a hard one. I don't know. Did anybody? What'd you get? Anybody think about this one? I'm sure some people did. The closure of Q. You were all nicely talking to each other in your breakout groups. Minus infinity to infinity, yeah. Otherwise known as R, I would say. So this is R, right? This is something we talked about last time. In this example, for Q, the limit points are all of R, and so when you make the closure, it would be Q, the original set, union with all the limit points. So it'd be Q union R, which is just R because Q is a subset of R. So I hope that's what you got for Q bar. How about this next one, 1 over n? The closure of that, it means you take the original set plus you add in any limit points. Can somebody else say what you said for that one?
Yeah, 0 to 1, closed set.
The interval from 0 to 1?
Yeah.
The closed interval? That's kind of the right idea, I think, although that's not quite right.
We had a union 0.
Yes, it would be the original set, but you add in just 0. This set is only values that look like 1 over n, so it does not include something like 2/3 is not in this set, and it's not in the closure either. The only limit point of that set is 0, and so you just add in that 0. So yeah, there isn't a better way to write it than this, really. It's the original set, union, 0, and that 0 technically should be inside those little squiggly things, because that's a set over there. Okay, excellent. What about n, the closure of n? You have to think about what are the limit points of n, and you add those points into it. What did you say? Anybody get that one?
It's just n.
Yeah, just n. In this case, n has no limit points. Remember, limit points, these are also known as cluster points or accumulation points. The points in n, they don't have any accumulation at all. They're all just evenly spread out, spaced out from each other. So n has no limit points, and so when you do that union with the limit points, there are none, and you just end up with n again. All right. What about r bar? That means you start with all real numbers, and then you additionally add in any limit points of those. What do you think? Any ideas?
Minus infinity to infinity?
Yeah, I heard minus infinity to infinity, also known as R. Yeah, R bar is R. R is already a closed set, and so when you take the closure, you don't get any new stuff. It's just the same as R. Or another way of saying it is that R, its limits points are all of R. So the definition of the closure with that union, it would be R union R, which is just the same as R. What about, anybody think of these last two questions? What if F is closed? Then what is F bar? The closure of a set which is already closed? It is F. Do you mind if I say? I'm going to erase the question mark and replace it with F. If your set is already closed, that means it already does include all of its limit points. And so when you try to union in all the limit points, that you don't get anything new. They're already part of the set. All right, so this is because F already includes its limit points. So you don't get any new stuff when you take the closure. The closure will add in all the limit points, but if the set is already closed, it already has all the limit points, and you don't get anything new. What about F bar bar? What do you think? This is not in the case when F is closed. Maybe I shouldn't have called it F. I just mean any set at all. Here, I'm going to change it to come on now. I'm going to change it to let's call it A. I don't mean to imply that it begins being closed. What did you think about this one? Did anybody talk about that one?
A bar?
Yeah, A bar. I heard it. Why'd you say that? I don't know who said that, but
Because A bar is closed.
yeah, right. This is because A bar, the closure, is closed. And then by the previous line there, since A bar is closed, so the bar of that will be equal to itself, because the bar of a closed set is equal to itself. The closure of a closed set is equal to itself. So since A bar is closed, its closure, which is A bar bar, is equal to A bar. All right. So it's not like the two bars cancel each other out. It's like one of them absorbs the other one or something. There's no such thing as taking a whole bunch of bars one after another, because you always just get the same thing forever. All right. This is all about the closure. Any questions about any of those? I hope that's. I hope that you're sort of building up some intuition for what the closure is all about. All right. Okay, let's talk about a very basic theorem concerning the closure. Part of this we have already sort of realized. It says given any set at all, not assuming that it's closed or open or whatever. First of all, there are two statements. A bar is closed, right? This I don't really want to talk about in detail, but we've all sort of come to that realization, I think. A bar is closed, and this is maybe more interesting. I do want to talk about the second part. A bar is the smallest closed set containing A. This is a true fact, and actually sometimes this is what people use as the definition of the closure, the smallest closed set containing A. It's true. This is a true fact about the closure, which I want to see if we can do the proof of this second part here. Actually, the first part is deceptively difficult. I'm not skipping it because it's obvious, although hopefully you are beginning to have the feel like this should be obvious. But there are some technical details to show that the closure is a closed set. If you throw in all the limit points, then you get another set. You may wonder if once I threw in all the limit points of the original set, did that create any new limit points which I need to additionally throw in? The answer is no. Once you throw in all the limit points, you don't create any new limit points which are now missing that weren't limit points before. But those are the details you have to check to demonstrate that first part of detail, which I don't want to get into. Let's just do the proof of the smallest part. All right. You have to think, first of all, what is even meant by smallest? Well, it means smallest in terms of being a subset. So in order to prove this part, the smallest part, A bar is the smallest closed set containing A. Our strategy is going to be let F be any closed set containing A. And then I want to show that A bar is a subset of F. This is what is meant by A bar is the smallest closed set containing A. It means if you had some other closed set, A bar will be smaller or possibly equal. So that's subset or equal to F. All right. This is the idea. Let F be any closed set. And we're going to show that A bar is a subset of F. Okay. What are you going to do here? How do you use the fact that F is a closed set? So F is closed. So it contains all limit points of F, right? That's what it means to be closed. F is a closed set, and so it contains all limit points of F. That means since A is a subset of F, because I said F be any closed set containing A, right? That means that A is a subset of F. Since A is a subset of F, what that means is F contains all limit points of A, right? Because we already said it contains all limit points of F, but A is just some of those points. So F also contains all limit points of A. And then what can we say about that? So if I let that set, let L be the set of limit points of A, then A is a subset of F. That was assumed. And also, I just said L is a subset of F. And so A union L is a subset of F, which means A bar is a subset of F. And that's what we wanted to show, right? So that'll do it. The closure is the smallest closed set containing the set that you began with. All right. Any thoughts about that? Questions about that? The closure. You just throw in all the limit points and you get a closed set. That's the closure. All right. Excellent. We got about 15 minutes left. I think that's enough for us to at least begin talking about the last sort of big thing I want to say about closed sets is the relationship between open and closed. So open versus closed. I have said many times, and we have seen the evidence, that these are not opposites. Open is not the opposite of closed, because it is possible to be neither, and it's also possible to be both. But there is a relationship between open and closed. They are complementary in the set theory sense. Remember what complement means in set theory? I will refresh your memory. So for some subset of the real numbers, A, the way our book writes complement is with a little C up there. This is A with a C means the complement. So this is, and the definition of that is just R minus A. In other words, this is all X in R, such that X is not in A. That's what the complement means. It is all the points which are not in A, all right? And in this class, we are always talking about real numbers, so we're only going to consider like in set theory, you have to have some kind of universal set when you take the complement. For our purposes, it's always going to be R. So the complement is written with the little c up there. A basic fact about the complement is anyone remember this fact? What is ACC? That's the complement of the complement. It is.
Just A?
It is just A, yeah. AC is all the things that are not in A. ACC would be all the things that are not in AC, which means they are in A. So this is A, right? This is a basic fact about complements. Okay? And complements give you the relationship between open and closed. So here's a big theorem, which we can talk about this, I think, in 15 minutes. There's two parts, although once you know the first part, the second part becomes very easy. It says a set O is open if and only if O complement is closed, and F is closed if and only if F complement is open. So this is the sort of deep and abiding relationship between openness and closedness. They're not opposites, but if a set is open, then its complement is closed. And if a set is closed, then its complement is open. So for example, if I have, let's say, O is the open interval from, 3 to 10. This, of course, this is open. What is the complement of that? It ought to be closed. That's what the theorem says, that the complement of an open set is closed. What's the complement of that? Well, you could, if you're having a hard time imagining this, my set here is from 3 to 10, right? This is the set O. The complement would be all the other stuff. That's this and this. So when I write the complement, it would be a union of two things. It would be, the thing on the left is minus infinity to 3 with the closed bracket. That's because 3 is not in the original set, and so it is in the complement. And then so that's half of it, and then union. The other half would be closed interval, or interval close at 10 up to infinity. All right? And I will just have you notice, this is closed, right? Each of those two things are closed intervals. They go out to infinity, but they're still closed because they include the endpoint. And then the union of two closed sets is closed. Did we talk about that? We didn't. I guess we didn't, but it's true. We are going to talk about that eventually, but not quite yet. Actually, this theorem is the easiest way to talk about that kind of thing. Anyway, this is a closed set, and I'm just trying to give an example of the theorem there. Another example would be something like N. N is closed. That's because N has no limit points. And when you ask, does it contain all of its limit points? The answer is yes, because there are no limit points. This is sort of true for vacuous reasons. Anyway, N is closed. What's the complement of N? Well, you could write it as a bunch of open intervals, couldn't you? I mean, on the picture, this is N, right? And the complement would be all of these open intervals in between. So this, I could say, this is a bunch of stuff, union with, say, -2 to -1, and then union with -1 to 0, union 0 to 1. These are all open intervals, right? This is the complement of N. It's all the numbers which are not natural numbers. But this is open, right? Because it's a union of countably many open intervals. All right. we've already talked about how any union of open intervals is open. Any union of open sets is open. Okay, we got 10 minutes. Can we, these are just examples. Can we actually talk about the theorem, why the theorem is true in our remaining 10 minutes? Let's see if we can do it. Let's just do the open part. So I want a proof of the open part. Maybe at the very beginning, it'll only take 5 minutes or so. At the very beginning next time, we'll just finish that off, do the closed part, even though I said we weren't doing any new stuff next time. You will allow it, I hope, because it's my class. I'm the boss. So remember what I wanted to show. This is O is open, if and only if O, the complement, is closed. Right? That's what we wanted to demonstrate. So let's do this way first. We're going to assume O is open. All right. And I want to show then that O complement is closed. What it means to be closed, of course, is that it contains all of its limit points. So I'll say, want to show that O complement is closed. And the way we do that is I say let X be a limit point of O complement, and I have to show that X is an element of O complement. That's what it means to be closed, right? It contains all of its limit points, So you take a limit point of O complement, and you have to show that that point is in O complement. The picture you should have in mind here is O is an open set. So let's just imagine that it's like an open interval here, right? That's O. And then O complement would be all of this stuff out here and over here. This is O complement. O is these things in here, all right? And I choose X to be a limit point of O complement, which means it could be, you know, over here, X, or it might be right up against the edge there, X. Anyway, it's a limit point of O complement. That means that every neighborhood around X contains some points of O complement. And then you have to show that X is actually in O complement. All right, anyway, since it's a limit point, X is a limit point of O complement. So that means any neighborhood V epsilon of X contains points of O complement. That's what it means to be a limit point. Any neighborhood around the point contains some other points of the set. Any neighborhood contains points of O complement. We have to say something about O. So far I've just said stuff over and over again about O complement. You have to translate this into saying something about O. But since the complement, I said V epsilon of X contains points of the complement. Another way of saying that is i.e. V epsilon of X is not a subset of O. When I say contains points of the complement, that means not all the points are in O, because some of them are in the complement, which is to say the neighborhood is not a subset of O, all right? So what we've demonstrated is that any neighborhood around X will not be a subset of O. Any neighborhood around X, like this, will not be a subset of O. That means X cannot be inside O because O is an open set. So since O is open, all points in O have neighborhoods which are subsets of O, right? That's what it means to be open. And this special point does not have such a neighborhood. So X cannot be in O. And that means, I said that as if it were the conclusion of the proof, but that means X is in O complement. And this is what we wanted to show as desired. right? Because I said before, I wanted to show X is in O complement. All right. This is the demonstration that if you have an open set, then the complement of that set is closed. It's a little something, I guess. Okay, we got 5 minutes. Can we just do the last part of this? The other direction is, I think, a little bit easier in my opinion. So that one was, I assume O is open and I want to show O complement is closed. The other way around, I'm going to say assume O complement is closed. And I want to show O is open, all right? To show that O is open means you take some point and you have to show that there's some neighborhood around that point which is a subset of O. So take any X in O, and I want to show that for some epsilon greater than 0, V epsilon of X is a subset of O. This is what it means to be open, that every point has a neighborhood which is a subset of the set you're talking about, okay? That's what I want to show, that there is some epsilon, which makes V epsilon of X a subset of O. All right, since O complement is closed, and X is in O, and X is in O, that is to say X is not in O complement, because that's the same, when I say X is in O, that means X is not in O complement, and O complement is closed. This means that X is not a limit point of O complement, right? O complement is closed, which means it contains all of its limit points, but X is not in there. And so X must not be a limit point of O complement. When you say it is not a limit point of O complement, it means that there is some neighborhood around X which does not intersect with O complement. So there exists some neighborhood, really there exists some epsilon such that V epsilon of X contains no point of O complement. That's the opposite of being a limit point, right? Limit point means every neighborhood contains some points of your set, but I just said X is not a limit point, which means there is some neighborhood which contains no point of O complement. But then if you just rewrite this in terms of O, what happened? My pencil. V epsilon contains no point of O complement. Writing this in terms of O, it says i.e. that V epsilon of X contains only points of O, right? If it contains nothing in the complement, then it must be all just points in your set O, which is to say, i.e., V epsilon of X is a subset of O. And that's what I wanted to show right up here. All right, so that's about it for our time. But this is the big thing about the relationship between open and closed. They're not opposites, but they are complementary. The complement of an open is closed, and the complement of a closed is open. Something which is not open or closed, its complement is neither. Can I just say one last thing? We got 1 minute left here, but that's enough to give one very important example, an important and weird example that we haven't talked about yet. Weird example is the empty set. Remember, R is open and closed, right? What about the empty set? We haven't discussed the empty set at all, but you can discuss it in terms of complements. Empty set complement. Can anybody say what is the complement of the empty set?
The real numbers?
Yeah, it is R, right? The empty set means nothing. The complement of that would be everything, and in our setting, everything means all of R. All right? And so what can you say then about the empty set being open or closed, or what? What do you say? I think you say R is open, and so its complement, another way, the empty set complement is R. It's also true R complement is the empty set, right? And the complement of an open is a closed. And so since R is open, it means the empty set is closed. And by the second part of the part that we didn't prove yet, but would you mind if I just for completeness sake, since R is closed, empty set is open. And so R and the empty set are both open and closed, otherwise known as clopen. And in fact, they are the only two clopen sets in the real numbers. It's a true fact, although we're not really going to get into that. All right, now I've gone over by 1 minute. I think I'm really done at this point. Okay, so next time, if you will allow me, just for a few minutes at the very beginning, we'll talk about complements of closed sets being open, which is the other part of that theorem. But I think that'll do it for today. I will see you all in person tomorrow.